Okay, in this video I'm talking about complex roots of polynomials, which is going to be a way for us to use the complex numbers that we were talking about last time. But I think that some of the things that we're going to do today may be a little beyond the scope of the CLEP exam. Specifically, the number and type of roots. I have not seen that type of question on any of the CLEP materials, but it's still good algebra. So we're going to just start with an example that you really already know how to do. Okay, so you solve this equation. This has got a squared in it, so it's it's quadratic, so I'm going to have to set it equal to 0. And then I'm going to try to factor it, and I'm going to think to myself, I'm going to think of any two numbers that multiply to 13 while adding to 4, and no, you can't. So we're going to have to use a quadratic formula instead. And since while we're at it, we're going to use it a few times today. I'm just going to write it down for everybody again, just in case you're, starting to forget. We know that if ax squared plus bx plus c equals 0, then x is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. So I could say in this case, x will be negative b plus or minus the square root of b squared is 16 minus 4 times 1 times 13 all divided by 2a. And so when you go and you actually do the arithmetic, you're looking for negative 4 plus or minus the square root of negative 36 divided by 2. And up to this point in the year, we'd kind of just stopped there and said, well, the square root of negative 36, that's not a real number, so we can just say no real solution. But now we know how to deal with the square root of negative 36, so we'll be all right. So what I'm going to do is I'm going to simplify this a little bit. Negative 4 plus or minus, well, the square root of negative 36 is square root of 36 times the square root of negative 1, which is going to be 6 times I. Okay, so I've got negative 4 plus or minus 6i divided by 2. And that's, for me, a safe place to stop. But if you had to simplify this farther, you could say that's negative 2 plus or minus 3i's. Because we would need to divide everything by 2. And what we're up against now is this fact, I'm sure it's got some sort of fancier name, but if a polynomial's got one complex root, the conjugate of that root is also going to be a root. So complex roots of polynomials always come in pairs. And specifically, the pairs are conjugates of each other. So let's say come in conjugate pairs. So looking back at this example, we saw that 2 plus 3i, or negative 2 plus 3i was a solution. And we saw that negative 2 minus 3i was also a solution. Okay, and those are conjugates. That is going to be true in general for all polynomials. Okay, that if you've got a complex root of one of them, of a polynomial, its conjugate will also be a root. And going back to this, I think you don't have to worry about this not being the case, but as I said, it's not necessarily true. This is complex roots of polynomials with real coefficients, always come in conjugate pairs. If you had a polynomial with complex coefficients, who knows what could happen? I could see a situation very easily where, a first-degree polynomial with complex coefficients could have a single complex solution. So this is true, provided we have real coefficients on the original polynomial. And so here's one, I think I'd like for y'all to try on your own. If you're watching at home, you should probably pause the video now because the answer's going to pop up real soon. All right, there you go. So this is a third degree polynomial, so we're going to need to start by trying to factor. Okay, see, I have a greatest common factor of x, so I factored that out, and I was left with x squared plus 2x plus 3. X squared plus 2x plus 3 is the type of thing that looks like it's factorable, but you would need that to be negative 3. Okay, so it's not factorable. You use the quadratic formula for that factor on the right. For the factor on the left, you could say, well, that thing would equal 0 if x was equal to 0. And then when you take it down, you're going to get the square root of a negative number. Simplify it a little bit. You're going to get 2 complex roots and 1 real root. All right, question from the front was about the second to last and the last step, like how we actually simplified the numbers. And so what I would think, I would take that square root of 8 and run it through the scientific calculator and get 2 root 2. So negative 2 plus or minus 2 square root of 2 times I divided by 2. But really what, like, this is like distributing in a half to both of those things. So this is 1/2 of negative 2 plus or minus 2 root 2I. So that when I distribute this in, I'm going to get negative 1 and just 1 root 2I. Negative 1 plus or minus 1 square root of 2 multiplied by I. And now I don't often do it in this class, but I am going to bring in the graphing calculator to show you all what this thing looks like. Actually, no, I'm just gonna draw a picture for you. Okay, so this thing, we know that it's got an intercept at x equals 0. It's like, what's happening there? And so really what this thing looks like is that it comes from below. It kind of, you know, has a little bend to it, but it goes up there. And it passes through at 0 with confidence, but it's got some bending action elsewhere. And so that's from our study of polynomials, we know that, you know, if it has only the 1 power of x right there, it's a single root, it's going to pass through with confidence, and that we are, you know, there's probably going to be 2 others somewhere, and the 2 others are complex. And so between the complex and the real solutions, we have a total of 3 solutions for this third degree polynomial. The next one I got for you is just a pretty straightforward one. X squared plus 9 equals 0. Definitely the type of equation that you could be expected to solve, you know, on a quiz or a test or something. And so what I'm going to do is I'm just going to, you could use quadratic formula on this with b equals 0, but I'm going to just try to directly solve. X squared is negative 9. When I take the square root of both sides of an equation, I need to remember the plus or minus. And the square root of negative 9 is the square root of 9 times the square root of negative 1, which is 3i. So x is equal to plus or minus 3i. Okay, this is 2 different solutions for a second degree polynomial. Last time we saw 3 different solutions for a third degree polynomial. In general, this is the fundamental theorem of algebra, an nth degree polynomial has n roots if you're counting multiplicities and complex roots and all the possibilities. Okay, so in general, you see a 4th degree polynomial, there's going to be a total of 4 roots. It could be that one was a triple root and one was a regular root. It could be that there was 1 double root and 2 complex roots. It could be that there was 4 regular roots. Okay, and then on the right, there's also a 7th degree polynomial. A 7th degree polynomial has 7 roots. Okay, so in general, this nth degree polynomial, n roots. Okay, to that point, I'm going to talk about y equals x squared. You know, how many roots should it have? How many does it really have? Okay, well, it's a 2nd degree polynomial, so I'm expecting 2 roots. But then you can also just, you know, draw a graph of this thing. I don't know what the graph of y equals x squared looks like. It's, you know, a parabola. It's, you know, nice looking parabola like that. And I'm only seeing 1 x-intercept, 1, 0, 1 solution, 1 root. But remember that this is a bounce here, which means that it was a double root. And we're also seeing that in the expression of the function. You see x squared, we see that that one factor repeated twice. So it has x equals 0, which has multiplicity 2. We say it's a double root. So counting multiplicity, this one has 2 roots. When looking at some other cases that we've seen, because we're pretty familiar with quadratics, here we have, one with 2 roots, 2 distinct real roots. And maybe I'm running out of space, but maybe I'll go over here and I'll draw one that kind of looks like that. And this one had no real roots, which means that it must have 2 complex roots. And if you think about what caused us to have no real solutions to a quadratic, it's because we were taking the square root of a negative number, which means that those are all of a sudden going to become complex roots. Okay, so this is 2 complex. Right, before I move on towards the questions about, drawing conclusions about the roots of polynomials based on their graphs, I just need to remind you something about the, the multiplicities. And so the question is, which of the following graphs could represent the polynomial f of x given by some number multiplied by x minus some number squared times x minus some other number to the 3rd power? Okay. Well, this squared here, this means we're going to have a bounce on the x-axis at x equals b, whatever that is. And then this x minus c to the 3rd power means it's going to have a 0 and it's going to have a sign change at x equals c, but it's going to be hesitant when it does it. Okay, so it's going to have a hesitation at x equals c. Okay, so the only graph on here that has a bounce and a hesitation is option B. Okay. Has a hesitation right here. Okay, so we'll call that x equals c. And it has a bounce over here at what will be x equals b. So this one could only be answer choice B. I just want to remind you about how the graphs of polynomials act at zeros with multiplicity greater than 1. Next example in your note packet is the sketch of a 4th-degree polynomial. I'm going to say that this is the sketch of y equals x to the 4th minus 16, just so I can do a little bit more with it. And it's shown. How many complex zeros does x to the 4th minus 16 have? Well, okay, I know that this polynomial needs to have a total of 4 zeros, because it's 4th degree. Right, 4 zeros, 4th degree. What I'm going to say is that I can see 2 of them right there. And they both have multiplicity 1 because they're just going straight through. They're not flattening out as they're going through the axis. Okay, so 2 zeros each with multiplicity 1. So that means that I need to have, I've got 2 missing. So they must be complex. Okay, so I must have 2 complex roots. And so I guess when I said 2 zeros here, I meant 2 real zeros. Okay, but I've got a little bit more to say on this. So x to the 4th minus 16 equals 0. This is the type of thing that we can kind of solve that a little bit. Okay, you can factor this thing using a difference of 2 squares. So this is x squared plus 4 and x squared minus 4. And x squared minus 4 is also a difference of 2 squares. So I could have x squared plus 4 x plus 2 and x minus 2. And this thing will equal 0 anywhere any of these three factors are equal to 0. Well, that means that this is 2 and that's negative 2. So, you know, I know where these are coming from. This is x equals negative 2 and positive 2. But the x squared plus 4 equals 0 when x squared is negative 4, which is going to pull us back to complex answers. Okay, so that's kind of what you've got going on. When you have, you know, maybe two real zeros and two complex zeros, is that it would factor down to something where you had, you know, nice factors, maybe even repeated factors, and then if you had some with larger multiplicity, and then something that was going to necessarily pull back imaginary, like x squared plus 4, or that very first second degree thing that we looked at where we just used the quadratic formula and it came back squared. Okay, so this is what's happening really behind the scenes. Okay, maybe they give you the sketch of a polynomial, or actually probably, you know, if you're looking at it, it's probably a nice figure. It's a graph that we produced, but I'm just sketching for you. I'm showing you a 6th degree polynomial. How many complex roots are there? Well, let's see how many real roots are there. Those are easy to spot. Here's 1, 2, 3, 4. This one is bouncing, so it's got at least multiplicity 2, and it definitely has even multiplicity. So I've got a double, 3, 4, 5, 6 total real roots for a 6th degree polynomial. And a 6th degree polynomial with 6 real roots, I've found all of them, meaning no complex roots are on this one. Okay. Let's see, 4 regular standard roots with multiplicity 1, and 1 with multiplicity 2, meaning no complex roots. Okay, another one. Question like, well, why can't a 5th degree polynomial have 4 real roots and 1 complex? Now, if you tried to draw this, you know, based on the end behavior, it would not be possible. You would see if you started off with just an x-axis and you tried to draw a 5th degree, you know, say with a positive leading coefficient, and it came from below and, you know, did some weird stuff. It's just not going to be possible. You may see it. It's from something I just kind of mentioned earlier. And it would be more if we had more like, you know, a bunch of practice problems with this. But the complex roots come in conjugate pairs. It means that they come in pairs, or there's always an even number of them. Okay, so we can't have one complex root. That's the problem. Okay, I'd say that, you know, complex roots come in pairs. Okay, another one, another kind of just like what if question or why can't question. Why can't a 7th degree polynomial have 4 real roots and 2 complex roots? Think about that for a second. Do you see why 093? So obviously it's got 2 complex roots, so it's not that they have to, there has to be an even number. There's something else going on here. So if you look at the total number of roots, a 7th degree polynomial needs to have a total of 7 roots. So I would say, well, the total number of roots needs to be 7. So you could have 5 real roots and 2 complex roots. But you can't have 4 and 2 because that would be only a total of 6. Okay, so we need 7. And I think I've got. Oh, okay, yeah, I've got a few more good ones. You know, practice problems for the quiz. in case you're still watching 20 minutes into the video. So this is a draw me a picture type question. Draw me a picture of a polynomial that's 6th degree and has 2 complex roots. Well, I'd say the easiest way to do that would be to just draw one that's going to have, the characteristics of an even degree polynomial, but only 4 apparent zeros. So what I'm going to do is I'm going to just be like, okay, here you go. I know since it's 6th degree polynomial, the arms have got to be going the same way, regardless of which way they're going. You could say it has a negative leading coefficient, make them both go down. But, maybe something weird has happened in there. Maybe sometimes, not always, but sometimes there's a little bit of weirdness that happens between 2 of the zeros or somewhere in there, a little wiggly aspect. And okay, I've lost my place. Over here with a 5th degree polynomial with no imaginary roots and 1 triple root. Okay, well, let me just make sure that's the triple root. And I'm going to start there. I know that with a triple root, it's got to slide through. And if it's 5th degree, okay, the arm's going to go in opposite directions because it's odd degree, kind of like a line. And so what I'll say is that it'll need to go up and then down. Okay, you could have made it bounce at this 0, kind of give yourself a double root. We didn't say anything about a double root, it said 1 triple root. So that would be a 5th degree polynomial with 1 triple root. All right, and the last one I've got for you is one where they're going to give you a graph. And it's going to say, here's a picture of all of the zeros of some function g of x. They'll also tell you, hey, by the way, g has 4 complex roots, or some other even number of complex roots. And they'll ask, what's the lowest possible degree? Okay, well, I can see 1, 2, 3, 4, 5. And if you can see the roots on the graph, then they're real, right? Because they're on the real number line. So if you can see these roots, they're real. I've got 5 real. Said 4 complex. And these are the ones that we can't see on the graph, giving us a total of 9 roots. And the fundamental theorem of algebra tells us 9 roots, 9th degree. It looks like that's cut off a little bit, but you get 9 roots, 9th degree. Nth degree polynomial, n roots, up to multiplicity, up to complexity.